Welcome to another lecture on complex variables and transforms. There is a small recap before we start today's lecture that f of s, the Laplace transform for any given function f of t, can be computed using this simple formula based on integration, and the limits are from 0 to infinity, and f of t, the Laplace transform of f of t, is calculated for t greater than or equal to 0. Right, this is what we studied last time, and we studied a number of f of t's. We tried a number of t's for which we calculated the values of f of s. Today we'll solve another interesting example on computing Laplace transform. We'll compute Laplace transform of cos omega t and sine omega t, and the Laplace transform of cos omega t we'll call it LC, and the Laplace transform of sine omega t we call SL sub s, where this S stands for sine and this C stands for cosine or cos. Right, so LC can be written as by putting this cos omega t as f of t in this formula, replacing f of t with cos omega t, and all the things remain the same, and the formula becomes this: integral from 0 to infinity cos omega t times e to the minus st dt. Right, now we apply the product rule. I have some 1 or 2 exclusive videos on integration by parts. I'll share that too on our YouTube channel in your playlist. Right, so how we apply integration by parts: we'll declare one of the two functions as the first function and the other as the second function. So let's declare this as the first function. We'll integrate that and we'll write the second function as such and apply the limits, and then we'll write whatever we have written here as the first function. The integral of first function, we'll write it here, and the second function will differentiate it. So the derivative of cos omega t is minus sine omega t, omega times sine omega t. In fact, this omega will be we can write it out of the integral because it's not the function of t. Right, so now we can put the limits here. If we put the limits, e to the minus infinity is 0, e to the minus 0 is of 1, cos 0 is of 1. Right, and we are left with a very interesting expression here: integral 0 to infinity e to the minus st sine omega t dt. This is LS, the Laplace transform of sine omega t. So we'll replace it with LS, the Laplace transform of sine omega t, because LC is cos omega t to the minus st dt. So LS has to be e to the minus st sine omega t. Right, so this is LS, the Laplace transform of sine omega t. Right, solving it further gives us 1 over s minus omega over s LS. Right, we have taken this s out of the integral because it's not the function of t. Right, so this is equation number 1, and let's solve this integral then. LS is Laplace transform of sine omega t. Putting it like this: e to the minus st sine omega t, and then applying integration by parts. The first function is integrated, the second function is written as such, applying limits minus the integral that we computed here. We write it here as such, and the second function, it is differentiated. So sine omega t, when differentiated with respect to t, is omega cos omega t, and omega is taken out of the integral because it's not function of t. Right, minus 1 over s, and then put the limits. If the minus infinity is 0 and sine of 0 is 0, so we have two zeros here: 0 minus 0, because sine 0 is a 0, e to the minus infinity is also 0, so 0 minus 0 is a 0, and plus omega over s. This minus and minus become plus, and this integral is this LC. So this integral is replaced with LC. So now we have LS it's all becomes 0, so LS is omega over s times LC. This is our equation number 2. Now we have two interesting equations: equation number 1 where LC is in terms of LS, and equation number 2 where LS is written in terms of LC. So we take the value of LS from equation number 2 and put it in equation number 1. In this equation, we'll replace LS with this omega over s LC. So if we do that, when solve it a bit further, we have LC here, so combining the coefficients of LC by taking this term on the left hand side, this becomes taking s square as the LCM, and then we have s squared here, 1 over s here, so s squared plus omega squared over s squared here, this 1 over s here, this s cancels with 1s, and LC can be written as s divided by s squared plus omega squared. That's great. So LC, we have computed LC. LC is the Laplace transform of cosine omega t. This is s over s squared plus omega squared, a very important expression. And then once we have computed the LC, we can straight away put that in equation number 2 here and compute LS, the Laplace transform of sine omega t. So Laplace transform of sine omega t is omega over s, and put LC here, this LC that we have just computed, s over s squared plus omega squared. So s cancels with this, and we are left with omega over s squared plus omega squared. So it's not very clear, but it is s squared plus omega squared, this one, omega over s squared plus omega squared. So this is how we can compute Laplace transform of sine omega t and cos omega t. That's all for this lecture, and the lectures to come we will keep on studying more about Laplace transforms. Thank you.